right, dynamics. So this is work done primarily by our friends in physics and applied math. And it's very important because the Snowball Earth turns out to be a very dynamic planet, has a dynamic atmosphere, dynamic cryosphere, surprisingly dynamic ocean. Even the mantle and lithosphere are influenced. And in many ways, the dynamics of Snowball Earth are counterintuitive. Okay? I think everybody thought that if you put an ice sheet over the ocean would tend to stagnate because the modern ocean needs winds. Also tides, but winds are very important in driving the overturning circulation and the mixing of the modern ocean. So people thought if you covered the ocean with ice, it would tend to stagnate. Turns out that's completely wrong. And it's completely wrong for very basic physical reasons. But that's why you need physicists, because they're very good at looking at a problem and boiling down a problem to the essential parts. Okay? And not thinking by analogy, which if you think about Snowball Earth by analogy with the present, you get into trouble very quickly. So I'm going to begin with this guy, Boudica. He was a very interesting character, and his many publications have been published in a series of books that have all been published in English. He was an early advocate of carbon dioxide, anthropogenic carbon dioxide in global warming. This famous climatologist here is looking at Boudica O'Reilly. He was actually a climate skeptic. In his time, which at that time was actually quite common, there were a large proportion of serious atmospheric scientists who were skeptical about anthropogenic global warming. There are very few today. There are lots of climate deniers, but very few climate skeptics. Okay. So, as I mentioned, Boudica was interested in the heat balance of the Earth and the water balance, and the Russians had really good data at that time, because science was strongly supported in the former Soviet Union. And so Boudica was often invited to the States for conferences, particularly about the polar ice balance. Even in the 1950s, there was a lot of concern, particularly in the military, about the future of the summer Arctic sea ice. In the Soviet Union, some politicians thought that getting rid of the Arctic sea ice would be a good thing for the Russian climate. Boudica was not so certain about that. In the United States, there were concerns that he might lose the cover for the nuclear submarines. So Boudica visited the States a lot and had a large impact on American scientists. And so his results were quickly confirmed in the United States. And Boudica was really one of the first people to do a global climate model. And basically, he did something very simple. He took something that's well known, like the variation in surface temperature from the equator to the pole. Okay, that would be what you would call a one-dimensional model. You try to write an equation that describes the variation in the mean annual zonal average, that is the average all around a line of latitude, temperature as a function of latitude. And now obviously, it gets colder towards the pole because of the angle of the Earth's surface with respect to the incoming beam. Also, you have to consider the poleward heat transport by the circulations of the atmosphere and ocean. In a one-dimensional model, you can't do real physics in that. You have to have some sort of diffusive approximation that fits the data well, and he did that. In a general circulation model, you can come somewhat closer to real physics. And also you have to consider the albedo of the Earth. Now, the albedo is the fraction of the incoming radiation that is reflected. It's useful to think of the co-albedo, which is the fraction that is absorbed. So when sunlight falls on seawater, about 90% of the sunlight is actually absorbed by the ocean. But if it falls on ice, and particularly if the ice is covered by fresh snow, up to 90% of the sunlight is reflected. And so when you freeze the ocean, you change the albedo in a way that has a very dramatic effect on climate. Clouds also have an important effect on albedo, but they're really not so important as ice on the surface because clouds have competing effects. So as you know, clouds make it cooler in the daytime but warmer at night. And that's because they reflect incoming radiation, which makes it colder, but they absorb outgoing radiation, which tends to make it warmer. So Boudica found that clouds were not so important, but ice on the surface was very important. And ice is more important than snow because ice is on the surface in summer. Snow generally is not. And of course, summer is important because that's when the albedo effect is most pronounced. So what Boudica found, and this was found quickly thereafter in climate models, is that there is no stable ice line equatorward of about 40 degrees latitude. Because at this point, so much of the incoming radiation is reflected that the surface temperature falls below freezing everywhere. And so you immediately go from this to this. This is not a stable solution. Okay? And this, in those days, this was called the large ice cap instability, or sometimes the white Earth catastrophe. And this is a very stable climate state. It's very difficult to get out of this. From a physics standpoint, virtually impossible. Maybe billions of years from now when the sun is much, much brighter. There's also a small ice cap instability. That was actually the one that the climatologists were most interested in, the potential to get rid of the Arctic sea ice, in effect. This is much more dependent on polar geography. This one is not so much. This is more robust. Okay, and as I mentioned, all modern, complex, sophisticated general circulation models also show the same instability. So we can look at it on a diagram like this. This is called a bifurcation diagram by our climate friends. And this is the ice line latitude, okay, in a one-dimensional model, as a function of the solar flux, so brighter or dimmer, or the equivalent carbon dioxide radiative forcing. Higher, lower concentrations of carbon dioxide. Okay. So with the modern solar flux and carbon dioxide concentration, we could be in any one of three stable climate states. We could have no ice, okay? We could be in the climate we're actually in now, or we could be in a snowball Earth. Could be in a snowball Earth today. It'd be very stable. These are the unstable regimes here in terms of the ice line latitude. This oscillation here would be like the glacial and interglacial cycles we've had in the Quaternary. And in the initial energy balance models, if you reduce the solar flux by a few percent, you went into snowball Earth. And this was a huge problem because nobody could understand why the Earth could be so vulnerable in a model to something that had never actually happened. Because no physicist believed that we'd ever been here. Because to get there, you would have to increase the solar forcing by about 25% to get out. And as you know, the solar variability is about 1/10 of 1%. So that was actually a big stimulus for climate modeling to try to figure out what was wrong with the models. They never found it. And the reason for that was because the solution wasn't in physics, it was in chemistry. Okay, so this is Jim Walker, and he and Paul Hayes and Jim Casting wrote this fundamentally important paper in 1981 on silicate weathering feedback. And basically it's because silicate weathering is temperature dependent. Okay, if it gets hotter, the reactions go faster, and also wet areas get wetter. And so weathering goes faster, and weathering consumes carbon dioxide. So if it gets warmer for some reason, then the weathering speeds up, and that limits the increase in carbon dioxide and stabilizes the climate at a warmer, but a state that is stable. Okay, so it acts as a sort of a thermostat. As it gets colder for some reason, the weathering rate goes down, and that allows volcanic outgassing to build up more CO2, and so it stabilizes the climate at a colder but a stable climate. And it has allowed the Earth to stay within the habitable zone over as long as we've had a sedimentary record, 3.8 billion years minimum, probably a lot longer. Okay? And at the end of this paper, because it's a fairly long paper, so a lot of people didn't get to the last page and they didn't read the statement. And so he just finished saying that this thermostat is probably what rescues us from the white Earth disaster. Okay, he's saying that this negative feedback from silicate weathering prevents the Earth from getting so cold that you have so much ice you reach the ice albedo instability. He says it probably protects us from that. But if it didn't, and it's possible that it wouldn't, because the silicate weathering feedback, although it's very effective, is very slow. Okay, silicate weathering feedback will consume all the anthropogenic CO2 we put in the atmosphere, but it will take, in total, hundreds of thousands of years, and even for the first 80%, many thousands of years. Okay, so it's not going to protect us, it'll protect the Earth. Whereas the albedo feedback, the climate consequences of changing the albedo, that takes a few months. Okay? So the silicate weathering feedback can't really police the ice albedo, which is a positive feedback, whereas the silicate weathering is a negative feedback because of the difference in the time scale. So they said if a global glaciation were to occur, the rate of silicate weathering should fall very nearly to zero. Okay? And that's because if the atmosphere is below freezing everywhere, there's no liquid precipitation, there's no rainwater. And CO2 is not soluble in snow. It's only soluble in water, in rainwater. Okay? So there's no way of getting the CO2 out of the atmosphere. Volcanoes will continue to emit CO2 in the atmosphere because plate tectonics will continue. Plate tectonics doesn't care if there's a kilometer of ice on the ocean. So volcanism will continue, but you can't get the CO2 out of the atmosphere. It's very little silicate weathering going on here. There is some silicate weathering in the ocean, but not on the continents. There's obviously not much primary productivity here either. So CO2 will accumulate in the atmosphere. And so what happens is that if we ever got to the ice albedo instability and dropped down to the fully glaciated state, GCM has estimated the ice line to advance in about 150 years to the equator. So now you're in Snowball Earth. Now CO2 has to build up, okay? From maybe 100 parts per thousand to this level, which is estimated to be between 10 and 100,000 ppm. Okay, 0.01 to a tenth of a bar of CO2. That takes a long time. Make a rough estimate, 10 million years or more. And then you reach this point here, and that's the point at which the CO2 radiative forcing finally overcomes the high albedo, and you start to open up dark water at the equator. Now, as soon as you start getting any dark water exposed, now that's absorbing much more solar radiation, so you have the positive feedback of the ice albedo driving the deglaciation, driving in the reverse direction. So remember, that's a positive feedback. And so you deglaciate very quickly. Okay? I say less than 10,000 years. My guess is it's closer to 1,000 years. We don't really know yet. And so we go from fully glaciated to no ice at all because we're at a very, very high CO2 concentration, but the surface is getting darker and darker as the ice retreats. And there are a whole bunch of other feedbacks as well. So now we're in the hottest climate the Earth has ever experienced. The immediate aftermath of this long-lived total freeze. And then over something up to maybe 10 million years, silicate weathering, intense at first, because you've got all this finely ground rock powder from the glacial action, which is high surface area, so it's very, very reactive. And all sorts of fresh rock lying around that weathers intensely. But very quickly you develop a mature weathering profile, and then you got to wait for tectonics to provide fresh rock. So the overall period of the CO2 drawdown may be as much as 10 million years, and then you're back sort of where you began. So what we see here is a hysteresis loop in CO2. And this is really at the heart of the whole Snowball Earth hypothesis, because this hysteresis loop makes strong predictions which can be tested geologically. That the onset and the deglaciation are globally synchronous. They're very, very rapid, geologically instantaneous. And the cryocron itself is long-lived and terminates under extremely high CO2 conditions. Okay? Now, those were the predictions that were made when no data existed, but those were the predictions. Okay, all that geochronology I showed you this morning postdates this hypothesis, which really comes out of the Jim Walker's 1981 paper. So Joe Kirschvink is the one who coined the term Snowball Earth and first proposed it for the Marinoan glaciation. He did it in a 7-paragraph extended abstract buried in the middle of a 1,400-page book, and then never wrote anything more about it for 10 years. Not a sufficient strategy to convince a skeptical readership of a radical idea. So I often referred to myself as Kirschvink's bulldog. How did this biomagnetist and paleomagnetist, Joe Kirschvink is founded the science of biomagnetism. That's the use of magnets by organisms from bacteria to whales for navigation and other purposes. The reason he got onto this was that he was part of the Precambrian Paleobiology Research Group, organized by Bill Schopf at UCLA. And there's Joe there. And you'll notice that Jim Walker was also part of that group, as was Joe Kirschvink. And also 2 of the experts on iron formation, Nick Bucas and Case Klein. And iron formations were very important, actually, in Joe Kirschvink's thinking. Joe's a paleomagnetist and a biomagnetist, so he thinks iron is the king of the elements. A number of Australians in this group, Roger Summons, Malcolm Walter, Bruce Runniger. I was not part of this group, I regret to say. I wish I had been. Okay, here are some of the dynamicists who have been really important in the last 15 years in helping us to understand what the predictions of the snowball hypothesis actually are in more detail, and how to really properly look at the geological evidence. So these are the more senior people who have been most active: Gilles Rumstein in Paris, Jochen Morotzky in Hamburg, Ellie Zipperman at Harvard, and Dave Ferrer at MIT. Ray Pierre Humbert at University of Chicago I might also put in there, but I chose these because of their outstanding students. So Yannick Donadieu is a student with Gilles, Eiko Feucht with Jochen, Brian Rose with Dave Ferreira, and Dorian Abbott with Ellie, and this is another friend of Ellie, Yossi Ashkenazi, who there's a whole new science that's just developed about the dynamics of the snowball ocean. It's a hot topic in physical oceanography right now. So one of the challenges about the idea of snowball Earth right from the beginning was that there's abundant geological evidence showing that the cryogenian ice sheets were dynamic. In other words, they were flowing. Okay, and that meant there was a hydrologic cycle. There had to be areas of ablation, that is, net diminishment of ice volume, and areas of accumulation, net accumulation. And so the ice was flowing from the areas of net accumulation towards the areas of net ablation, just like any glacier. And some of this evidence has been known for a long time. So here from 1891, scratch marks and a moraine ridge in the northeast of Norway, Finnmark, from a period much older than the last ice age, by Hans Royst and the director of the Norwegian Geological Survey. And here is this moraine, and it sits on a polished and striated glacial pavement with 2 directions of ice flow. So dynamic ice, both from the evidence from the moraine and also from the striated pavement. And these are not uncommon in the cryogenian. So that's clear geological evidence for dynamic ice. So that means the ice has to be thick. Okay, it has to be thick enough so that it's at the pressure melting point at the base, so it can slide. And in Greenland, that's about 3,000 meters in thickness in the central part. The ablation zone is this zone out here, and this is the accumulation zone. And so the ice is flowing from here to here. And to give you some idea of the scale, Alfred Wegener, who died on the surface in 1930, his body is right above there. So this is a profile of the temperature of the ice Okay, not the paleo temperature, the present temperature of the ice at the center of Greenland at summit and near the center of the East Antarctic ice sheet at Vostok. Dome Sea is indistinguishable from Vostok. And surprising to most geologists, because for years people said, couldn't be Snowball Earth because we have evidence of meltwater at the base, and of course you wouldn't have meltwater in a Snowball Earth. Notice that in the lower 1,500 meters of the ice, including the base of the ice, the Antarctic ice is 10 degrees warmer than the Greenland ice, despite the fact that Vostok is nearly minus 60 at the surface, whereas summit is just over minus 30. Okay? So the surface temperature is much colder in Antarctica than Greenland, and yet the lower part of the Antarctic ice is much warmer than that in Greenland. And the reason for that is the difference in accumulation rate. So at Vostok, because it's so cold, the accumulation is extremely slow. Whereas in Greenland, being much closer to open water and warmer, the accumulation rate of ice is much faster, and as a result, there's a faster downward advection of cold ice. So, of course, Snowball is probably even going to have slower accumulation than Vostok, so Snowball ice will tend to be warm ice. And note that Vostok, it's nearly 500,000 years at the base because of the slow accumulation, whereas in Greenland, it's much younger. It's only 100,000 or so. Incidentally, that's the cold LGM, last glacial maximum ice. This is the warmer Holocene ice. That's the reason for that bulge. This is the LGM ice, cold ice going down. So counterintuitively, Snowball ice will tend to be warm, effectively because it's accumulating extremely slowly, so there's more time for geothermal heating to warm the ice. It's true there's less frictional heat production in Snowball because the accumulation rates are lower, but it looks like the age of the ice is a more critical factor. Okay, I first want to talk about the Snowball atmosphere, because of course that's what's transporting the water vapor that is allowing the ice to grow from ablation and accumulation. And you're always going to have that because some areas are going to be warmer than others. Now, the Snowball atmosphere is extremely dry, but it's not dry because the ocean is frozen. It's dry because it's cold. So the saturation vapor pressure in equilibrium with the surface goes down as the temperature goes down. It doesn't make any difference whether you have ice or cooled water. It hardly makes any difference. And in fact, the latent heat of sublimation, which is a direct conversion of ice to water vapor, is only about 15% greater than the latent heat of evaporation. Okay, so the Snowball atmosphere is dry, but it's dry because it's cold, not because the ocean is frozen. There's ample sources of water vapor. Now, the dynamics of dry atmospheres is of great interest to planetary atmospheres people because all the other planets that we know have dry atmospheres. Okay, we're the only one that has a wet atmosphere, and it's called dry convection. And it's very interesting, and they can't believe their luck that we actually have it in the geological record because dry convection turns out to have some interesting properties. So what we're interested in as geologists is how the water moves around, the hydrologic cycle. And as you know, in the present, this is precipitation minus evaporation. So net precipitation is positive in blue. Net evaporation in orange is negative. And so at the equator, this is paleolatitude from north to south, the strongest net precipitation is at the equator. Everyone knows that you have forests along the equator, the equatorial zone, and in the mid-latitudes, but in the subtropics you have dry belts. Now, as it turns out, Snowball is exactly the opposite. So there's the present in the dotted line, and this is Snowball. Note the difference, the tenfold difference in scale. So this is net precipitation in water equivalent, net sublimation in water equivalent. And in the Snowball condition, the driest and the most negative accumulation is at the equator, and the highest rates of snow accumulation are in the near subtropics. Okay, so the equatorial zone and the subtropics are completely reversed. Just like they were with high obliquity, but for a completely different reason. Notice also that outside of the equatorial zone, there's positive accumulation in Snowball Earth all the way out to the pole. Okay, so the ice on Snowball Earth is snow-covered and very slowly accumulating at high latitude, but accumulating from about 20 degrees either side of the equator all the way to the pole. Okay, so you have a very large accumulation zone where you're going to have very, very white ice because of fresh snow. And then you're going to have this rather narrow band of a blade of ice, darker ice, straddling the equator. The accumulation rates of water equivalent are up to a few centimeters per year in the subtropics, but only a few millimeters per year poleward of that. But remember, a millimeter per year doesn't sound like much, but that's a kilometer in a million years. Okay, so here, in this zone here in particular, you grow ice that's thick enough to reach a few thousand meters in thickness, so it's wet and dynamic at the base quite quickly. Within a few 100,000 years, ice sheets in Snowball Earth will be dynamic. So they'll be dynamic, according to models, for most of the snowball period. Okay, so this is the striking situation, that you have a blade of ice at the equator and the potential for dry land, and then snow-covered ice poleward of that. Now, the reason for this funny situation where the driest point is at the equator, so this is P minus E at low CO2 at the beginning of the snowball and near the end of the snowball, high CO2. So as you can see, the difference amplifies. You know, the ablation rate gets higher here and the accumulation rate gets higher in the subtropics, but the shape doesn't change. These are 6 different GCMs. One of them, this one, foam, is an outlier. And it's because it doesn't have any cloud condensate in the model, which is very important in snowball. It's the principal absorber of the outgoing infrared. So the reason for this funny situation is that in dry convection, the Hadley cell upwellings are very, very confined to exactly the surface area where you have the maximum insulation. It's because you don't have much convection because of the dry atmosphere. You don't have any latent heat that's helping to drive the convection. So convection is very, very weak. So the temperature, you know, in the modern, the temperature is broadly constant across the tropics. But in the snowball, the hottest area is exactly where the insulation is highest. And so this narrow band goes back and forth across the equator during the seasons. And also the surface, because it's solid, has very little thermal inertia. It doesn't have much memory, okay? Because you can't stir up, you know, new water because it's solid. So it's like Mars or the middle of Asia. It's a very continental type climate. So as a result, the upwellings are very narrow, and so whenever the maximum insulation zone is away from the equator, which it is most of the time, the equator is actually in the downwelling. And as a result, when you look at the mean annual here, and so these are the flow lines, and the solid lines are going this way, and the dashed lines are going this way. And so in the mean annual, the equator is in a downwelling, and that's why it's more evaporative, because you've got cold air that's descending and drying out as it pressurizes. I should also point out that under snowball condition, because of the dry convection, the troposphere is quite thin. It's not much more than half the depth that it is now. And that's also allows the Hadley cells to be quite confined. Now, last year, some very important model experiments were published in a paper by Doug Ben, who's a glacial sedimentologist. The modeling was actually done by a French guy named Guillaume Lahire, who's based at Paris at IPG. And for the first time, they ran an atmosphere ice sheet model, no ocean, because he ran under snowball conditions, so the ocean is entirely ice covered. in this model, but he ran it at different levels of CO2. So that's 100 ppm, 200 ppm, 50,000 ppm, and 100,000 ppm. And so that's the range of CO2 that models suggest would have occurred in the snowball. And the surprising thing that emerged from this is that at no time were the continents completely ice covered. And in fact, the ice sheets got smaller as the CO2 rose. The hydrologic cycle was spinning up. Okay, it's much stronger here at high CO2. So the ice sheets are moving faster, but they're actually getting smaller. And so this has, it turns out, and I'll tell you this afternoon, has very important implications, I believe, for biology. That there are always sources of dust in Snowball Earth. Okay, the afternoon session, the climax is going to be all about dust. This is consistent, I think, with some geological evidence that previously was puzzling. So here in South Australia, at a place called the Cattle Grid, it's been described by George Williams, you have a glacial surface. It's a block field, Felsenmeer, overlain by an aeolian sand sheet, the Whyalla Formation, and there are deep sand wedge polygons. And these develop in periglacial soils as a result of the warming and cooling effect during the seasons. And these were recently studied by Ryan Ewing and co-authors, and the deformation structures associated with these sand wedges showed that the ground surface temperature could not have been very far below the freezing point, and therefore you must have been very close to the deglaciation, yet this surface was not ice covered. It was exposed to the atmosphere, otherwise you'd never have these cracks, because the seasonal temperature would be insulated by the ice. So this was an ice-free surface near the termination, and that helps to, these models help to explain this. This is in Svalbard in Arctic Europe, and here we have some carbonate beds. This is the cap carbonate here, the end of the glacial termination. Within the glacial sequence, there are some glacial lacustrine lake deposits, lake carbonates. These lake carbonates have two important characteristics, both involving the isotopes of oxygen. The mass-dependent isotope fractionation is very strong, and the oxygen is heavy, up to plus 15 per mil. That means these lakes were not ice-covered because you have to evaporate water to make the water isotopically heavy. If those lakes were ice-covered and you were sublimating the ice, you could get very saline lakes, but isotopically they would actually be depleted, not enriched, because of the ice-water fractionation. The ice is 3 per mil heavier in equilibrium than water, and when you sublimate, there's no fractionation, and because of the low diffusion rate in ice. If you sublimate a centimeter of ice, you sublimate it completely. There's no fractionation. So you'd actually be taking off heavier isotope, and that would drive the water lighter rather than heavier. So the fact that the delta O18 is heavy shows that these lakes, at least part of the year, were ice-free, so you have to be close to deglaciation. And I'll describe this afternoon in session 3, the mass-independent isotope fractionation between 16, 17, and 18 oxygen shows that CO2 was extremely high, and therefore close to termination. And once again, no ice sheet. Okay, so this modeling result that shows that the ice sheets actually diminish. Instead of covering the continents completely, the new modeling suggests sort of counterintuitively that the ice sheets get smaller even as they're speeding up, are consistent with these geological observations. Another geological observation, which for many years was said to be inconsistent with snowball Earth, is the presence of cycles in the geological deposits. Cycles indicating repeated advances and retreats of the ice line. Okay, so the ice advance and the stuff becomes coarser and coarser, and then you're completely under ice, and then you get a retreat. And people said, oh, well, snowball Earth would be a very stable climate, and you wouldn't have this kind of repetitious cycling, which in the Quaternary is well known and is mostly of orbital origin. So here we have cycles. So there's a till, represents deposition under ice. The ice steps back. You have proglacial marine deposits, well stratified, and grading upwards into till again. Here's one of these gradational contacts. The ice rafted drops down up into a massive till or diamond. So in the same paper, Ben et al., Guillaume Leire, for the first time, ran the model with precession-like forcing. It wasn't real precession. He switched back and forth between warm summer and cold summer orbit. And so there's the warm summer orbit in the northern hemisphere, the cold summer orbit in the northern hemisphere. The white, this is just this part blown up. The white line is this ice line, and then the cold summer orbit is this ice line. You notice the ice line is going back and forth on a precession timescale. That's 10,000-year timescale for precession by 5 degrees. That's 550 kilometers. That's a big migration of the ice sheet. And this depiction here shows in red the areas of positive mass balance when you go from warm to cold, and the blue are the areas of negative mass balance. And as you'd expect, there is hemispheric asymmetry, which you expect in precession, because the seasonal precessional forcing is an opposite sign in the two hemispheres. So there's more blue in the southern, more red in the northern. However, there's both blue and red in both hemispheres, showing that the response is actually quite complex and showing great sensitivity to changes in the atmospheric dynamics and the hydrologic water balance just by small changes in the orbit, which, remember, have no effect on the total annual sunlight we receive, but only how it's distributed over the seasons. So no inconsistency between the snowball state and depositional cycles. Okay, that's the atmosphere. Any questions on that before I turn to the yeah?
As always, I have a question. How dependent are these models on the paleogeography? And so I guess the models that Doug ran, he has the majority of the continents either near the equator and mostly in the southern hemisphere. You split those continents where you have, I guess, land free across the equator. How significantly does that shift the models?
I think it has a big impact on the carbon cycling, but not on the atmospheric dynamics. At least not in Snowball, because remember, in Snowball, it's all land. Okay, so you've got a solid surface everywhere. It doesn't really make that much difference. I guess the albedo of the continental areas will be lower. And as I'll argue this afternoon, the ablative ice may be darker than in those models. I'm going to talk about something called cryoconite this afternoon, which are meltwater ponds on the surface of the ice because of the accumulation of dust. If it's true, all these models will have to be rerun with a lower equatorial albedo. But I think the thing that will probably be altered the least will be the atmospheric dynamics. And that's fundamentally a product of having the ocean frozen. I don't think the presence, the distribution of the continents is really going to matter too much other than for the albedo. And of course, the albedo will become more important if, to the degree to which the ice sheets are diminished and more bare land is exposed. So it would tend to become more important as the snowball progresses. I think that model actually that shows the deglaciation, my guess is that that's too extreme. And when cryoconite is put in the model, that will be, the shrinking will be less. But that's just a guess. And my guess has almost always been wrong.
Yes, and you mentioned that you've got the high carbon dioxide concentration prior to Snowball, and then... No, after.
After?
Yeah.
Well, what I was getting at about this period, the conventional wisdom is that the photosynthesis in the Proterozoic that reduced the carbon dioxide atmosphere by creating oxygen that allowed the explosion of higher life forms in the Cambrian. So if you have a higher carbon dioxide concentration during that period, whether it's before or after, does that suggest that there are also extraterrestrial effects in
Yeah. Okay, now I understand the question. Yes, it is true that CO2 would have been higher in the Neoproterozoic than it is today because the sun was dimmer. Okay, the silicate feedback, the way the silicate thermostat works is by adjusting the atmospheric CO2 such that the sources of carbon dioxide are equal to the sinks. Okay? That's actually how it works, by adjusting the CO2 level. And so because the sun was dimmer in the Neoproterozoic, CO2 would be higher. Okay? So if you lower the CO2 in Neoproterozoic time to the present level, we would go into Snowball Earth. Because we needed more CO2 to prevent that.
So what you're saying is it was dimmer, there was less radiant energy.
About 7% less than present. That's right, yeah. But because there was more CO2, that meant the CO2 lever is a little less sensitive, because to get a climatic effect, you have to make a bigger change. Yeah, so the silicate weathering feedback would have been less strong at that time than it is today.
I'd like to ask a question about the temperature at the time of Snowball Earth. Given that you put an Antarctic temperature there down to minus 60, what was the temperature?
I'll show a slide coming up that will show that exactly at low CO2 and high CO2 at different latitudes in 6 different GCMs. Yeah, so that will be coming up. Okay. All right, so I'd like now to talk about the ice that's on the ocean, because after all, the ocean is most of the surface of the Earth, so this is the most important. So as you would expect, the ice is thicker at the pole than it is at the equator. This is North Pole to the equator. There are 2 types of ice. Note that the ice is very thick. It's up to 1 kilometer. If the ice was static, the polar ice would be about this thick, and the equator would be quite thin. But that is dynamically unstable, and the ice flows, okay, just like an ice shelf. And so this is a sort of a dynamic steady state, and the arrows are indicating the flow lines within the ice. And you'll see there are actually 2 types of ice. There's marine ice, which is frozen seawater, okay, and that's freezing on here because the flowage is making the ice thinner than it would like to be. And so you're continually freezing on here and then melting here, because here the ice is thicker than it wants to be. So you've got a cycle of freezing and melting that's producing marine ice. Marine ice doesn't have air bubbles, so if it was ever at the surface, it would be quite dark. It would have a significant effect on surface temperatures because it's darker. But at least in this model, all of the ice at the surface is meteoric ice. That's compressed snow. Meteoric ice has a higher albedo because there's lots of air bubbles. And it has an accumulation zone, which is poleward of about 20 degrees, and then a zone of net sublimation. Okay, and so the ice is coming up here, being sublimated, transported by the atmosphere, and accumulating here. Remember Now, we thought that as the CO2 rose, the ice would tend to get thinner, and indeed it does, but it doesn't get any thinner at the equator. And the biologists were always hoping that the ice would get thin enough in the equator you could actually do photosynthesis under the ice. 700-meter thick ice is not good news if you're an alga. But actually, as you go from cold, low CO2, to warm, high CO2, but still in Snowball, these are the ice thicknesses. This is a model from Elliot Zipperman, fully dynamic ice model. The equatorial ice really doesn't get any thinner, and the reason is that as it gets warmer, the ice gets softer. Okay, because the coldest ice, or the stiffest ice, is at the surface. And as the surface warms, that ice gets softer and it flows more readily. So although the overall ice, global ice thickness decreases a little bit, the ice thickness gradient actually is reduced, and also the ice doesn't speed up because the gradient is smaller. So that was a bit of a surprise. Some people suggested that there were places where the marine ice actually could be exposed in the equatorial zone, and because that's darker, that would have a significant effect on the climate and make things warmer. And then climate dynamicists said, oh yeah, but that couldn't be a stable state because you would be removing seawater, because marine ice is frozen seawater, but you'd have no way of getting it back to the ocean. Because the marine ice that is sublimated will fall as meteoric ice, and so the meteoric ice would grow, and the marine ice would eventually run out of seawater, and so it's just not a stable solution. But that's because they didn't have continents. And if you put in a continent, which has an ice cap on it, this ice is very thick, and so you're producing meltwater here, and this meltwater is going back into the ocean at the grounding line, and so now you have an unstable situation because you're getting rid of meteoric ice into the ocean without any way of getting it back to the atmosphere unless the marine ice is actually exposed. So once you put in models, the whole situation gets reversed. And in fact, to have a stable solution, you have to have marine ice exposed. So because marine ice is darker, that means there is the potential for rather thin ice at the equator, still frozen, but thin. Okay, so here's the slide you were looking for. This is the annual mean temperature, surface temperature. The dashed lines are for high CO2 and the solid lines are for low CO2. And this is from the South Pole to the North Pole. There's the equator. Okay? And this is January. Okay, so austral summer. And once again, now you're at pretty much at the melting point in the austral summer in this depiction. And these are the different GCMs that have been run. This is actually an experiment called SNOWMIP, the Snowball Intermodel Comparison. So the climate dynamics people, they really like this snowball business because it allows them to run different models under identically prescribed conditions and then compare the model results. And that's a very good way of revealing how the models differ, and then to think about, why these different models don't give the same result under identically prescribed conditions. These models are so complicated, and they're bought off the shelf that it's not always obvious, why the model does what it does. And so it's very nice to be able to do these intermodel comparisons. This is the ice thickness at low CO2 and high CO2, and this is the ice velocity. Okay, so fastest moving ice is in the subtropics, well, in the low latitudes, in the tropics. Okay. So this has been called the sea glacier. This is the floating ice, and it's thick, and it's behaving like a glacier. It's flowing from the accumulation zone to the ablation zone, okay, but it's floating, and so it's often called a sea glacier. So that's 100,000 ppm, and in the mean annual, you're still not at freezing.
So just back to the temperature and the carbon dioxide effect. What you have is you have dry ice, obviously, and so that's going to limit the concentration of carbon dioxide in the atmosphere. Dry ice is what, 230 Kelvin, is that right?
Yeah, so it is possible that at low CO2, early in the snowball, there is actually dry ice accumulation in winter, in the polar region. However, that will disappear in summer. And so there is a sink, but the sink is equal to how much CO2 can be deposited in one hemisphere in 1 year, in one winter season. So it's a limited reservoir. That's what it looks like from back of the envelope calculations. It has not been investigated in detail, and it's an interesting question because, of course, it's a moving target. As CO2 rises, it's getting warmer, but on the other hand, the condensation temperature is going down because of the increased concentration. I think it would be an outstanding honors project for someone to actually do that. The back of the envelope calculation suggests that it does not prevent a barrier to getting to 100,000 ppm. Yeah, actually, Joe Kirschvink already did those calculations in his 7-page abstract. He discussed that. Yeah, Joe knew a lot more than he let on. Now, there has been a lot of interest in the climate dynamics community in trying to see whether there actually are some stable solutions which have low latitude ice lines, okay, in defiance of the sort of classic ice albedo instability. And there are two solutions that actually are stable under limited conditions in general circulation models. The first is called Jormungand, and that was shown to be a stable solution in a couple of GCMs by Dorian Abbott, who's now at the University of Chicago. He did that as part of his PhD work. And he did something very simple, and that is, he said the blade of ice is darker than ice that has snow on it, and so therefore we should give it a different albedo, a lower albedo. And if that albedo difference was large enough, as the ice advanced towards the equator, as he sort of ratcheted down the CO2, that ablative ice zone became wider as it entered the subtropics, the downwelling arm of the Hadley cells. And that had a sufficient effect on the planetary albedo that it actually stabilized the ice line at around 15 degrees of latitude. And he proposed this as a so-called Jormungand solution, where you actually have a stable band of open water. And of course, that, I think paleontologists would, were jumping up and down, very happy about this situation, because Snowball Earth seemed to them to be impossibly exclusive of photosynthesis. Okay, it seemed to defy okay, so where I would agree with them is that if Snowball Earth means that there is nowhere where sunlight, liquid water, and nutrients coexist, then Snowball Earth is false. I would agree with them on that. As it turned out, the model that showed Jormungand to be a stable solution was a model that did not have sea glacier dynamics. And when you incorporate sea glacier dynamics in the model, the Jormungand solution destabilizes, and the ice lines just go to the equator. And the reason for that is that sea ice dynamics is very important for two reasons. First of all, the free-floating ice transports latent heat. It soaks up a lot of energy melting that ice, and that makes things colder, away from the ice front. And the second thing is when that ice melts, it produces meltwater, which has low density, so it sits at the surface, and that reduces the heat capacity of the ocean. It's more difficult to stir up warmer water from depth because you have this low-density water that has lower salinity and freezes more easily at the surface. So both those things make it easier for the ice line to advance, and that destabilizes Jormungand. Also, Jormungand has not been run in different orbital configurations. Now, last year, a second stable state was proposed by Brian Rose, who's in the State University of New York in Albany, and he called this water belt. And this, like Jormungand, was a stable band of open water from about 20-25 degrees to the equator, but for a different reason. And in his model, that was the MIT general circulation model, as the ice lines converged on the equator, the Hadley cells intensified. They narrowed and intensified. This is not in Snowball, but this was a narrow band of open water. The Hadley cells became very intense, and so you had increased wind-driven mixing. Okay, and that increased the heat capacity of the ocean, because it meant you had to cool the whole ocean rather than just the surface. And that actually stabilized in that model the ice line at this low latitude. Okay. So that was an interesting one. And although this hasn't been demonstrated in the model yet, here's, I think, where it'll get unstable. When you have a lot of ice, like this, in the winter hemisphere, the surface gets extremely cold because you're radiating and you're receiving very little sunlight. The sun is low and you have high albedo. And so you're losing a lot of radiant energy, so the surface gets very cold. And if you've ever lived in Canada, you know when it gets really cold, what happens is you get an inversion. You get cold air trapped beneath warmer air. Remember, in the troposphere, normally it gets colder as you go higher. If you get cold air at the surface, that's very stable. Okay, and I remember Jim Walker mentioning this. He gave a paper called Strange Weather on Snowball Earth. And he said, the winds are howling aloft, but at the surface you do not feel them. And it took me years to appreciate the significance of that statement. And the significance is that if you have an inversion, you decouple the winds from the ocean. Okay, and so the wind-driven mixing is paralyzed. And these models, because these are long integration times and very simplified models, these models have only a few layers in their atmosphere of the model, and so they can't resolve a temperature inversion that's very close to the ground, maybe only a few decameters thick, boundary layer inversion. So I suspect, although, and Brian agrees with me on this, that's likely to destabilize this. So I really think the snowball is the more stable solution, and as it turns out, it makes predictions which these other two solutions do not predict a large hysteresis. So the high CO2 that we observe, I'll tell you about in the next lecture, the cap carbonates, which are a function of the high CO2 through ocean acidification, are not explained by these models.
Excuse me, you talk about the decreased wind, but surely you get very strong katabatic flows. You're going to have a higher, well, I'm just thinking what it's like in Antarctica. They get really, really strong katabatic flows coming out from the centre.
Yeah.
Because of the decrease in elevation of the ice.
Right, but those also be warm winds because of compression. So the McMurdo dry valleys, are dry because of katabatic winds, and those winds actually reach the freezing point in summer. So they're also going to go above the boundary layer. So when I lived in Calgary, I could go out on a sunny day when it was well above freezing in my shorts and a t-shirt, but if the cold air came in underneath that, the wind's still blowing up there, that warm air, but at the surface, suddenly you're at 20 below and you've got frostbitten ears in about 10 minutes. Yeah, so you're right, those winds will be blowing, those katabatic winds, and George Williams has clear evidence for it in the wind directions in the Waiala Aeolian sand sheet in South Australia, but they wouldn't feel the surface if you have an inversion. Because you got warm air, you got cold air that's stable beneath that warm air. Yeah, good question though. Okay. All right, the ocean. So this is potential temperature, seawater, Atlantic, Pacific, Southern Ocean. There's a wind-driven mixing, the Southern Ocean. It's the only place where intermediate water is exposed. And so wind-driven mixing is very important in the overturning circulation of the modern ocean. And that's because the modern ocean has this cap of low-density warm water. So I think everyone, including me, including most climate dynamicists, thought that if you covered the ocean over with ice, the ocean wouldn't feel the winds, and so the ocean circulation would tend to stagnate. Okay, and there were many articles written about the tendency for stagnation and stratification of the snowball ocean. Okay, but we failed to think about it from a very basic way. The modern ocean needs wind-driven mixing because it's being warmed at the top. Okay, and that's increasing the stability of the stratification by putting low-density water over high-density water. But the snowball ocean isn't being warmed at the top. At the top, it's only losing heat by diffusion through the ice. The only place where the snowball ocean is being warmed is at the bottom, by the geothermal heat. And if you warm a fluid at the base, it convects. Okay? So it turns out that convective mixing in the Snowball Ocean is very strong. And the Snowball Ocean is almost completely unstratified and isohaline. Okay, so here's some model experiments that came out a couple of years ago. So here is potential temperature. That's from south to north, near South Pole to North Pole. This is a mid-ocean ridge with a concentration of heat source. This is the sea glacier. Okay, so this is the water column. So you got warmer water here than here, but notice the scale. This is the difference between minus 3.4 to minus 3.6. In other words, the entire ocean has a temperature contrast of 0.2 of a degree. It's almost completely isothermal. And that's because it's well mixed. The mixing time is estimated to be maybe half of the modern ocean. This I think, is the salinity. Okay, so a little bit more saline at the high latitudes than here, but once again, the salinity contrast is between 49.5 and 49.2 parts per thousand, so less than a part per thousand variability in salinity. So this is an ocean that is actually unstratified and well mixed, and the dynamics are extremely interesting. So here's the equator. This is the zonal velocity of the water. That's the east-west velocity. And westward motion is red and eastward motion is blue. So just under the ice, the circulation is characterized by jets that are going in opposite directions. It's like a thruway or highway with cars going in opposite directions, very close to the equator. And because the ocean is unstratified, instead of being, when these jets run into a continent, instead of going sideways, they turn up. Sorry, they turn down. And when they're moving away from a continent, the water comes up to feed them. Okay? And so when they're running towards a continent, yeah, they turn up. And they cause the ice to be thinned, and there's all sorts of cavitational effects of this thinner ice producing meltwater, and you get pulsation, and you get strong upwellings where these jets are directed away from the continent. This is that is the vertical mixing, and you can see the vertical mixing is very, very highly concentrated right at the equator, although the entire ocean is also reasonably well mixed. So the mixing time is about 500 years, something on that order. And the mixing rate is in the meridional overturning is somewhere in the range of around 30 spheredrips.
Well, how does that compare to today?
Okay, so the meridional, just the meridional components, I think I said 30, is more like 20, so it's 20 to 30. So for comparison, the North Atlantic meridional overturning is 17 or 18 spheredrips. Spheredrip is a cubic meter per second. Global runoff is 1 spheredrip. We will be using spheredrip again in a different context. So it looks like the overturning circulation is at least as strong as in the present ocean. And basically it's because there's no heating of the ocean at the top. Okay, so here are the ocean dynamics in a 3D model. That last one was a 2D model. This is 3D model results. So once again, this is the zonal. So this is westward flowing, eastward flowing, blue, westward flowing, red. This is the vertical mixing, and this is the north-south velocity. So most of the action is at the equator. Away from the equator in detailed models that have recently come out by Malte Janssen at University of Chicago, there are whole lines of little jets in the zonal jets. It looks a lot like the atmosphere of Jupiter, the snowball ocean circulation. So it's a fascinating world that has just been started to be investigated in the last 2 or 3 years. The first model was published by Dave Ferreira at MIT as an appendix in a paper about 3 years ago. And I think there are about 4 papers now in press on various aspects of snowball ocean dynamics. So the ocean, nearly isothermal and isohaline, well mixed, salinity anywhere up to 2 times whatever it was when there was no ice. And because of the high salinity, the temperature is quite cold. Okay, so the modern freezing point is what, minus 1.7 or something? And the reason for all this is the geothermal flux. Okay, so now this very dynamic snowball ocean, I think, has some geological implications, one of which involves iron formation. So it's been known for a long time that in the Cryogenian, that this return to iron formation after a billion-year absence, that these are intimately associated with pretty proximal glacial deposits. So it looks like the ice margins or the ice grounding lines and the iron formation deposition are closely associated. And that was a bit of a puzzle. They're not in areas where you would expect low sedimentation rates. As you can see, there's lots of coarse debris here. Okay. Now, the idea that was originally proposed by Joe Kirschvink was that you cover the ocean with ice and it stagnated and became anoxic because there are sinks for oxygen but few sources because of the absence of organic productivity and burial. And this allowed ferrous iron to build up in solution. And when the snowball deglaciated, then the ocean became ventilated, oxygenated, and the iron crashed out as iron oxide. That was the original idea. And this was supported by Nick Bucas and Case Klein in the only paper that really came out right after Joe's 1992 abstract and supported Snowball Earth. It turns out this actually doesn't fit the geology very well. So here are the big iron formations in northwestern Canada and Snake River in the Rapitan group. So here are the pre-glacial carbonates. There's the base of the glacial sequence. Here's the top. It's you'll notice it's over 4,000 meters thick, and the iron formation is down here near the bottom. It's not associated with the cap carbonate at all. So it doesn't look like the iron formation is associated with deglaciation. It is, however, closely associated with very proximal ice grounding line deposits. So there have been a number of suggestions why you had this return of glacial deposits. The first by the Namibian geologist Henno Martin in 1965, which he said that the ice cover caused stagnant bottom waters to be anoxic. That was basically what Joe said many years later. Then Don Canfield and Rob Raiswell pointed out that under snowball Earth conditions, you would have very little runoff from the continents. You'd have some meltwater, but it would be highly attenuated relative to non-snowball conditions. And runoff is the main source of sulfate to the ocean. And sulfate in anoxic waters gets reduced by microbial iron reduction, and that sulfide titrates out iron in the form of pyrite. Okay, so in the absence of sulfate input, there wouldn't be much bacterial sulfate reduction, and therefore the iron would remain in solution and could precipitate as iron oxide wherever oxygen was available. Okay, and one place where oxygen would be available would be in meltwater. Because meltwater from an ice sheet would have oxygen because the ice has air bubbles, and if there's oxygen in the atmosphere, there'll be oxygen in the air bubbles, and therefore in ice sheet meltwater will be oxygenated. And of course the meltwater will come out at the grounding line, right where all the debris is being deposited, and so you have the oxygen right where the glacial deposits are, and if the ocean is full of reduced iron in solution, that iron will precipitate as iron oxide right around the grounding lines. So I imagine these meltwater plumes not being gray like they are today, but red. An additional factor is that if you have a large sea level fall, that changes the chemistry of hydrothermal vent fluids. It changes the iron to sulfur ratio in favor of iron. So the source of iron goes up, the source of sulfur goes down as a consequence of the sea level fall. So that's another factor that, that is consistent with the presence of iron formations during these severe glaciations. Now here's an interesting story. So this is in the McMurdo Dry Valleys in East Antarctica. This is the Taylor Glacier. Taylor was an Australian geophysicist with Scott. And this glacier is pretty flat here, and it's probably because it's floating, because I think there's a water body underneath there. And that water is seeping right there. And that's called Blood Falls. And here's what it looks like. There's a tent for scale. And it's red, of course, because of iron oxide production when that meltwater hits the oxygenated atmosphere. Now, they've done this group, Joe Mikuchki and co-authors have drilled into this and got samples of this water, and it has a most remarkable chemical composition. It's very acidic. It's very cold because it's very saline. There's no detectable oxygen. And it has 3.5 millimolar of iron. That's 1,000,000 times more iron than modern seawater. It also has 50 millimolar of sulfate. Now a modern ocean has more sulfate than any ocean in history probably, but almost 30 millimolar. This is even more sulfate than the modern ocean. And who would have ever thought that sulfate and iron could coexist? Because normally if you have sulfate, you'd have microbial sulfate reduction, which would produce sulfide, which would titrate the iron as pyrite. But that's not happening here, and the reason is because the water is covered by a glacier. Incidentally, no hydrothermal source of this iron. It's just coming out of granitic country rock, because it isn't even sitting on the Ferrar Dolerite, as far as I can see. Unless there's a dike, feeder dike. That's possible. They've not been mapped. But. So, because there's a glacier above this water, it's dark, and so there's very, very little organic productivity. There is some, there is an ecosystem there, but it's not producing very much organic matter, so there's not enough organic matter to sustain microbial iron reduction. Okay, the iron reducers have to have organic matter to live on. And so there's lots of sulfate, but there's no sulfide, and so iron and sulfate can coexist because of the low, because someone turned the lights out. So I'd like to think that the water underneath the Taylor Glacier is sort of like Snowball Ocean in microcosm. And so here we would have the meltwater plume, okay, and it would have oxygen, and we have a ferruginous acidic brine, and where these two waters meet, I would suspect would be where the iron formation is forming, precipitation of ferrihydrite. Okay, and this is consistent. I don't want to go into much detail on this, but this is Galen Halverson's work from northwestern Canada showing isotopic gradients and cerium anomaly gradients that are consistent with formation of the iron at a redox front between ferruginous anoxic waters and oxygenated waters. Okay, so I envisage something like this. And the point here is that in the open ocean, because it's well mixed, you would not be able to have a stable redox boundary between oxygenated water and ferruginous water because of the mixing. You need to have protection. And so only in something like a fjord or a rift basin or something, some semi-restricted basin where you're protected from this strong mixing in the main ocean, could you have a stable redox stratification and the precipitation of iron and accumulation of iron formation. So I think that that may be why, and these authors have suggested that that's why the iron formations are so spotty. I mean, that was one of the problems. Why don't you have iron formations everywhere in the Sturdian? You don't. They're just, and they're mostly in semi-restricted basins. Okay? And I think that's why, it's for a reason we never thought of, and that is that you needed protection from the strong mixing in the open ocean. So I think this is an example of where the modeling allows us to look at an old geological problem in a completely new way. Okay, so there's the distribution of the iron formations in the Sturdian. Okay, so here's, I think, what we can conclude at the present time, and a lot of work is being done, so some of these conclusions may change. So the atmosphere is characterized by dry Hadley convection, and the annual mean state, the Hadley cells are reversed. So the net sublimation zone is at the equator, and the maximum accumulation zone is in the subtropics, exactly the opposite of any climate where there's liquid water, including Jormungand and water belt. They're all normal, but Snowball is the reverse. The ice sheets, tropical ice sheets flow fast but lose mass as CO2 rises. Their mass balance is sensitive to precession-like forcing. Okay, lots of cycles. Sea glacier, it's thick, and it flows gravitationally like an ice shelf from the areas of accumulation to the areas of ablation. And, but it doesn't actually speed up, unlike the ice sheets, which do speed up as CO2 rises because of the softening effect. Makes the ice more uniformly thick and reduces the gradient that's actually driving the flow. And the subglacial ocean is unstratified and well mixed, and has lots of interesting dynamics like these subequatorial zonal jets. I didn't say anything about the lithosphere here. There's interesting studies that suggest when you deglaciate, you get a big increase in subaerial volcanism because of decompression. On the other hand, you would get a suppression of marine volcanism because you're loading the seafloor with more water. So there are these competing effects on magma production rates in the continents and the oceans. And potentially that would be a way of looking at the relative CO2 outgassing between continental and oceanic volcanism. That would be a good thing to know, and I don't think we know it very well at present. Because CO2 outgassing is something by volcanoes is almost impossible to estimate from observations because volcanic activity is so erratic and episodic. Okay, and I think that should be the lunch break slide. So are there, do we have time for? Yeah.
I just wanted to know, you showed the, cheers. I just wanted to know that you showed the ocean circulation at the equator.
Yeah.
And you had these jets going across in eastern, western directions. Just wondering how that changes laterally as you get closer towards the polar regions, and whether they would be affected by any other hydrothermal activity?
Closer to the polar region?
Yeah. So would those jets decrease in...
The zonal jets appear to become weaker as you move away from the equator.
Okay.
Yeah. In this model, of course, they had to arbitrarily put in the mid-ocean ridge, and they put it in at low latitude. But that was meant to be consistent with Lee's paleogeography, where the mid-ocean ridges in the model are associated with the Rodinia breakup.
Okay.
Yeah, so and it's a point worth making that all of these 3D models that need to have a geography, they're using Lee's paleogeography.
Is it possible that it could become stagnant poleward then, if these jets are decreasing in velocity? Yeah, so the circulation is going to be more sluggish, and as you may have noticed, the salinity was highest away from the equator. So the mixing away from the equator is more driven by Coriolis forcing. Okay.